I'd like to introduce our student award winner, Dr. Clara Wanjura, who was at the Cavendish Physics Lab in Cambridge, got her PhD there, is in just the final stages of getting those 3 letters attached to her name. She's now moved to the Max Planck Institute for the Science of Light at Erlangen in southern Germany. And she's going to talk about the topological framework for directional amplification. So, Clara.
Thank you very much for this very nice introduction, and thank you once again for awarding me this prize and giving me the opportunity to speak to you today. As was already mentioned, the title of today, I will be talking about 2 concepts, topology and directional amplification. Now, don't worry if you don't know anything about either of these, as I'll be going through them step by step. Topology is a mathematical concept that characterizes different shapes. In this particular instance, it will be very simple. We will just be considering curves like this one, and we will be interested on whether they wind around a specific point or not. So in this case, we will be considering whether this curve winds around the origin, so where these 2 axes cross or not. So for instance, here in these 2 cases, the winding number would be 1, even though the curves don't look exactly the same. And in the other case, the winding number is 0. Now, this is all very abstract, but what I've shown is that it is possible to identify a notion of topology in certain physical systems, and that just identifying this topology, we can decide whether a physical system displays a specific phenomenon or not. And this phenomenon is the one of directional amplification, which I've illustrated here on the right. Now, what does that mean? Directionality or non-reciprocity means that when we probe a system, meaning we send light through the system, a signal gets transmitted through the system in one direction, but is blocked in the reverse direction. And combined with amplification, this means that in the forward direction, this signal is amplified, while in the reverse direction, it is still blocked. Now let's, as you can imagine, directionality and non-reciprocity are interesting for applications. And one is optical communication. As I'm sure you are aware, much of our internet communication works through an optical network. And for this, it is important to route these signals in a network of optical fibers without the signals straying from one fiber to the other. So it is important that signal splitting and merging works in a clean way. And here, non-reciprocal elements become important. It's also important to protect lasers, because when we generate a light signal with a laser and send it in this optical network, some of the light will inevitably be reflected back off the optical elements in the network and re-enter the laser. However, this can lead to overheating and make operation unstable, so it is important to have a non-reciprocal element here to protect the laser. There is another application of non-reciprocity, and that is in the realm of quantum information processing, and this is where my work becomes particularly important. Now, here on the left, you can see an image of one of IBM's quantum computers, and as you may be able to tell from this image, this is a fairly large device, even though the actual quantum chip only sits down here. And all the rest that you can see is intended to cool this quantum chip down to very low temperatures. And the reason why we cool them is to prevent noise from destroying our quantum information that is stored in a qubit. Qubit is a minimal unit of information in a quantum computer. However, we still need to be able to read out this qubit. And we need to be able to do this while protecting it against noise. So one way how this could work is that light is emitted from the qubit and we record it here with some measurement electronics. However, measurement electronics also are noise sources. So noise will inevitably travel back. And if we don't do anything against it, whoops, now I did what I was told not to do. Right, I hope this works again. So if now the pointer isn't working, well, you can see, I suppose. So if we don't protect this, the noise will destroy our quantum information. Now, if we instead, this is not working. Okay. Sorry about that. Okay. Okay, now it seems to be working again. So if we instead add a so-called isolator, which is a device with a non-reciprocal transmission, then the signal can be read out. So it can travel in this direction, but noise can't travel back. So this is protected in that sense. Even better is when we have a directional amplifier so that we can amplify these fragile signal sources, weak signal sources or weak signals, while protecting the qubit against noise. So how do we obtain non-reciprocity in directional amplification in practice? An example for an optical network that allows us to do this is the following. Now here, each of these circles represents a resonator. Think of a resonator as a device with two mirrors so that the light can bounce back and forth and it creates a standing wave. And so this is one of these circles represent. And the light can then travel either from one resonator directly to the other and to the output, or it can travel via another resonator down here. And when these two paths recombine, there is the option of constructive or destructive interference. So what does that mean? So think of light as a wave, as I've illustrated here on the right. Now, if a peak align and a valley align, and these two waves come together, then the resulting amplitudes will add up and we obtain our original signal. However, if one wave is shifted against the other so that a peak and a valley align, we just get zero. And that's the destructive interference. And we can engineer these structures in such a way that we obtain constructive interference in one direction, but destructive interference in the other direction. And now we come to topology, but for that we consider larger structures and we combine multiple of these small networks that I just showed you to form a chain. And in this limit of the chain, we can define this topology based on the mathematical description of the time evolution of these systems. And we can distinguish three distinct regimes. So if the topology that we identify is such that the curve that we identify encircles a certain point, namely the origin, we obtain directional amplification. So here is an illustration of the field amplitudes. In one direction it's amplified, in the other it's blocked. Then there's the case of simply non-reciprocity, in which case the curve is still a loop, but it doesn't encircle the origin. And then we still obtain non-reciprocity, so the transmissions are asymmetric, but there is no possibility of gain. So transmission is at most one. And finally, in the last case, when this curve shrinks into a line, the transmissions are even equal in both directions. So much about theory. There are multiple platforms for realizing such systems in such a way that they are scalable and relevant for quantum technologies. For instance, with optomechanics, these are small-scale experiments where an isolator was realized. This is an example for a directional amplifier where the gain is much larger than the reverse gain, as you can see here. And new developments now also allow to realize large lattices. We have pursued a slightly different approach with a group in Amsterdam, in collaboration with the group of Ewald Verhagen at AMOVC. And we've realized such a system for mechanical vibrations rather than light modes, as I showed you now. And we've been able to essentially perform a proof of principle. Here, this is the topology that corresponds to what we realized in the experiment. And here you can see the experimental data. So when we probe at one end, we see the amplification in the other in one direction, but isolation in reverse. And here we see, in this other case, we obtain non-reciprocity. So, and with this, I would like to thank most of all my PhD supervisor, his former postdoc, and our collaborators with whom we did the experiments that I showed you just now. And thank you very much for your attention. I'm looking forward to your questions.
Thank you, Clara. Are there any questions? Yep, just one upon. Hang on.
Thank you very much. Could you give me some idea of the size relevance here? Because presumably if you're using a laser in astronomical terms, it doesn't matter what comes back, it will be very minute, but it's very small.
Yes, so the reason why I kept it very general is that the framework that is at play, or the topological aspect, is very general. So it is independent of scale. So you could have classical systems, quantum systems, you would still find the same underlying principle. But for it to be relevant to quantum information processing applications, you can see in these examples here, for instance, there's an there you would want to be sure that really almost nothing is reflected back. Even when you read out a superconducting qubit, for instance, you don't want a microwave signal to scatter back. And so here, if you look at this plot, for instance, you see an isolation of 20 decibels. So that would already be sufficient for these kinds of applications. Yeah, if you're working with optical networks for classical communication, you wouldn't need to go to that scale, I suppose. And also there are other ways to do it. In this case, you can use magneto-optic effects to break time reversal symmetry, if you know about this. In any case, and this is, however, this is leads to very bulky devices. So this is something you wouldn't want to do to put on a quantum chip, also because the magnetic fields are quite harmful for quantum computers. So this is why in this case you will need a different approach, and it's very important to understand the mechanisms at play, or to have some, and our topological framework now also gives us a handle to come up with new designs, for instance, for such isolators in this context. Yeah, thank you.
Thank you very much, Clara. I never actually understood how a qubit is read, but you gave a very clear explanation. And I always wondered why you didn't get things going backwards from the monitoring equipment and destroying the coherence of the qubit.
But they are
so that was
actually already used in superconducting circuits, and as far as I'm aware, because I think otherwise it would be very tricky.
Yeah, that's very good. And I'm sure decoherence and noise are very important in barriers in quantum computing at the moment. So
for sure.
I should just mention, I should have done at the beginning, that Clara, as well as winning the CSAR Student Award Prize, also, well, we're lucky to have her here because she's just been in Warwick accepting the Institute of Physics Theory of Condensed Matter Prize for her work, and has also won the award from the Cavendish Laboratory for the best PhD. So well done.
Thank you.